Please speak loudly.
My name is Oleksandr Chumak, and I am from division of magnetism from ON32, and I would like to present the report The Long Road to Maxwell Equations, some kind of historical report. So my presentation will conclude introduction, premises, Maxwell's time, and Maxwellians. So introduction. If you wish to pay the homage to the great physicist James Clerk Maxwell, you can find a few places for this. And there are fitting monuments to this person who developed the first unified theory of physics, who shows that electricity and magnetism are intimately connected. But no one from these monuments can reflect that fact that at the time of Maxwell's death in 1879, his electromagnetic theory, which underpins so much of our modern technological development, was not yet on solid ground. And he did a lot of work. Because of an extraordinary amount of information about the world, can be boiled down to 4 element questions. At first time, it was 20 questions, there were 20 equations, but at the end, there were only 4. So it took nearly 25 years for a small group of physicists themselves obsessed with them.
This actually is a common statement that there are 4 Maxwell equations, which is mathematically incorrect. There are 4 formulas, but they are not 4 equations, because at least 2 of them are the vector equations, which in 3-dimensional world are there are 6 of them, yes. Right? So there should be 8 equations.
Okay.
Anyway, it's a great progress from 20 to 8, but nevertheless.
And 4 formulas. And very elegant formulas. In comparison with the first one.
Everybody says 4 equations, but
yes, correct. And without the force of this group of Maxwellians, it might have taken decades more before our modern conception of electricity and magnetism was widely adopted. And that would have delayed all the incredible science and technology that was to follow. So today we learned that the light is just one piece of electromagnetic spectrum whose radiation is made up of oscillation electrical and magnetic fields. And the change in magnetic fields creates an electric field, and current and the change in electric fields give rise to the magnetic fields. But we have Maxwell to thank for these insights. But they did not occur at him suddenly and out of nowhere. The evidence he needed arrived in bits and pieces over the course of more than 50 years. So, premises. We can start our clock from 1800, when the physicist Alexander Volta reported the invention of a battery, which allowed experimenters to begin working with continuous direct current, because it's very important for this topic. Some 20 years later, there was Hans Christian Ørsted experiment, who obtained the first evidence of link between electricity and magnetism, by demonstrating that the needle of a compass would move when brought close to a current carrying wire. Next.
Maybe before you proceed, one should realize that at the time of Ørsted, the compass was one of the very few instruments physicists had in his laboratory, because there were not so many instruments available yet. So he just happened to have one standing next to his...
Especially in electricity and magnetism. Yes.
But how elegant were those devices?
I can make you one if you want.
Yeah, but compare it with this ugly computer. There was some those people had some feeling of art.
Soon after this experiment, it was also very fine experiment made by Andre who shows that two parallel current carrying wires could be made to exhibit a mutual attraction or repulsion depending on the relative direction of the current. And next, 10 years later, there was Michael Faraday experiment who showed that just as electricity could influence the behavior of a magnet also could affect electricity. When he showed that drawing a magnet through a loop of wire could generate current. And this observation gives me evidence of behavior that no one really understands in a systematic way. And what was electric current really? How did the current carrying wire reach out and twist the magnet? And how did a moving magnet create current? Major seed was planted by Faraday, who imagined a mysterious, invisible electrotonic state surrounding the magnet, what we would today call a field. He posited that the changes in this electrotonic state are what cause electromagnetic phenomena. And Faraday also hypothesized that the light is electromagnetic wave. But shaping these ideas into one complete theory was beyond of his mathematical abilities. It was a state of affairs when Maxwell came to this scene. So Maxwell's time. After graduating from the University of Cambridge in England, Maxwell set about trying to make more mathematical sense of Faraday's observation and theories. In his initial attempt, the article was called "On Faraday's Lines of Force," and Maxwell devises a model by analogy, showing that equation and mathematical apparatus for uncompressible fluid flow could also be used to description unchanging electric and magnetic fields. His work unfortunately was interrupted by a flurry of distractions. He changed a few jobs. He contracted smallpox and nearly died before finally taking a new job as a professor in King's College London. And somehow in all of this, Maxwell found the time to flesh out the Faraday field theory. Also, not a complete theory of electromagnetism, a paper he published in several parts proved to be an important stepping stone in the philosophy magazine and Journal of Science. It was building on the previous ideas. Maxwell envisioned a kind of molecular medium in which magnetic fields are arrays of spinning vortices. Each of these vortices is surrounded by small particles of some form that help carry spin from one vortex to another. But perhaps most crucially, it laid the groundwork for a new physical concept, the displacement current. But Maxwell displacement current is more fundamental than that. It can arise in any medium, including the vacuum of space, where there are no electrons available to create a current. And just like a real current, it gives rise to a magnetic field. So also Maxwell needed a few properties or constants to measure. And he used combining of them to obtain the estimating speed of electromagnetic wave in vacuum. And after that, he compared this value of speed of light in vacuum and concluded from their near equality that light must be an electromagnetic wave.
Can I make a comment? I kindly suggest you people read these words. Each of these vortices is surrounded by a small particle. Remember when we were talking about the quantum Hall effect, about the Chern-Simon theory,
It
And
will
about
be
the
next week.
anion,
Next week will be.
yeah, anions, that's another way around. There's a particle which is associated with the flux of a magnetic field, and that is a building block of the Chern-Simons theory, or all the mumbo jumbo, which is called the Hall effect theory.
Where did he get vortices from?
He made the vortices. We have to jump slightly forward. He had written the equations, right? We will soon see those ugly equations. And he solved them and find out that the waves, which are the solution for the free equations, are transverse waves. And at that time, people thought only about the waves propagating in a medium.
Water.
But all the media have both longitudinal and transverse waves. So he had to write down what is called a constitutive equation describing a medium in which all the transverse waves can propagate. And that is one of the possible models of a medium in which the wave equation will only have a transverse wave solution. There is another model which was prepared by another Scottish mathematician, Maxwell'a, which is even more complicated, but somehow more realistic physically, because there are no vortices in them. But that is the basic, that they had to invent the medium in which this electromagnetic field, as we call now, is propagated.
It was ether.
It was, well, he even didn't call it ether. But anyway, that's a beautiful picture, isn't it?
And it was a very useful mechanical concept, mechanical description. But later, Maxwell compiled the last pieces of his electromagnetic theory in 1864, and he left the mechanical model behind, but had the concept of displacement current. Focusing on mathematics, he described how electricity and magnetism are linked and how, as properly generated, they move in concert to make an electromagnetic wave. This work is the foundation of our modern understanding of electromagnetism. Unfortunately, this theory was met with extreme skepticism, even from Maxwell's closest colleagues. For example, one of the biggest skeptics was Sir William Thomson, Lord Kelvin. A lot of physicists just simply didn't believe that some kind of concept as displacement current could exist. And this is a big difference between physics in Victorian era and nowadays. Today we are willing to accept physical theories such as quantum mechanics so long as they are mathematically rigorous and have a great predictive power. So at that time he published his equations without any mechanical models. And don't say how these mystical electromagnetic waves could possibly propagate. For many of his contemporaries, this lack of a model made Maxwell's theory seem grievously incomplete. And you can see.
Can you come back two slides before, one more before? And I just want to point out that at the time when he published this paper, there was already telephone cable connecting Great Britain with Brazil. The telegraph was already used for 40 years by Morse. Telephone was already there, and all those things work according to Maxwell equation principles.
There means some part of the world.
At least some part of the world, but anyway, that part of the world comfortably use those devices without having underlying theory.
We will talk about the telegraph when we come to another hero of the talk.
Okay. So, at this slide you can see 20 Maxwell's equations as the first form, and you can see that one more leg of this theory is that it was very complicated. Not only for students of universities of the time, for the future of physicists, but also for contemporaries. And the net result of all of this complexity is that when Maxwell's theory made its debut, almost nobody was paying attention. But a few people were. So Maxwellians. And one of this small group of Maxwellians, of people who understand this, and accept this theory, was Oliver Heaviside. He obtained Maxwell's treatise at 1873, and said that I saw that it was greater and greatest. I was determined to master the book and sent it to Rome. The key was eliminate Maxwell's strange magnetic vector potential. I never made any progress until I threw all the potential overboard.
So maybe we will say a few words about the Mr. Heaviside. It's remarkable that there were two heroes of the modern electromagnetic applications. It's Heaviside and Edison, and both started their life as just the operators of a telegraph. Heaviside was, he actually hadn't even finished the school. He was only attending the school until he was 16, and then he didn't have enough money to pay for further education, but fortunately his uncle on the mother's side was this fellow who invented the bridge, electric resistance bridge, Mr. Wetzel, and he found him a job somewhere in Newcastle as an operator of a telegraph office. So Heaviside was working as a clerk there, and he learned mathematics and everything by himself. And the fact that he was a clerk in the office made it impossible for him to be a member of the kind of association of the electric engineers in Great Britain, because they wrote in answering his application, we do not allow the clerks to join our society. And finally they let him be there when he was already the fellow of Royal Society and many other things. And Heaviside was incredible because this was a man who once said that, well, shall I refuse to eat dinner because I have no thorough knowledge of how my digestive system works? So he was building up a mathematics, not paying any attention whether this mathematics has any sense or not. For example, he invented, he was the first man who used the complex numbers to describe the electric circuits. He then invented a method of solving ordinary differential equations by what is basically a Laplace transformer. It's called operator calculus. So he was able to solve complicated electric circuits by just solving linear equations, not differential equations, but algebraic equations. So in a certain sense, he was absolute genius. He, as a child, had also scarlet fever, which left him with a permanent hearing impairment, which makes, as he used to write, his life very easy, because he didn't listen to the idiotic statement of his colleagues, as he wrote in his memoir. So that's really a remarkable individual. And today we use the Heaviside function, the function which is 1 for x greater than 0 and 0 for x less than 0, and the derivative of Heaviside function is a delta function. As a matter of fact, he also invented the delta function, Dirac delta function, but learn how to operate it. So, but it's there.
So at 85, Harrison then reformulated Maxwell's core of equation into the four elegant equations we use today. So there was slide. Next, so if Harrison modified Maxwell's equation in this degree as we use today, why don't we call them Harrison equations? It's a problem. I can read it. So he wrote that if we have good reason to believe that Maxwell would have admitted the necessity of change when pointed out to him, then I think the resulting modifier theory may well be called Maxwell's. So because he called it Maxwell's, but himself. And let's continue. The elegance of equation is one thing, but the experimental evidence for Maxwell's theory was something else. When Maxwell passed away, his theory was incomplete, and there was no empirical evidence that light is an electromagnetic wave, but only one thing that that the value of the speed is nearly equal to the value of speed of light. And then there were a few people more who accepted this theory and decided to find these experimental evidences. And there were George Francis Fitzgerald and Oliver Lodge. Once they met in Dublin before 1 year the Maxwell days, they decided to collaborate and between each other and with Oliver Harrison. They then developed some circuitry that would be capable to convert low frequency electricity to high frequency light. But at the end, Lodge and Fitzgerald realized that schemes would create radiation of too low frequency to be detected by eye. But 10 years later, Lodge suddenly was performing experiments on light protection when he noticed that.
So, maybe we should also make a comment that Mr. Fitzgerald is this fellow from Lawrence Fitzgerald contraction. He was a Scottish physicist and mathematician who invented many things, but he really had another job. His family, he inherited the family business of making whiskey, and that basically was his main occupation. He had to take care about it, and apparently he was the inventor of slight cheating, how to produce a quality whiskey by importing. We will have a special seminar about it, but there are basically 3 types of whiskey. There's a Scotch whiskey, there's an Irish whiskey, and there's American bourbon whiskey. And the bourbon whiskey, which is made from corn, was considered to be inferior. The Irish claimed that and Fitzgerald was Irish, they claimed that their whiskey is much better than the Scottish whiskey. And that was due to special way of how the whiskey was seasoned in the barrels. And those barrels were very expensive. So one of the stories is Mr. Fitzgerald was importing the bourbon barrels, which were very cheap from the United States. And well, anyway, he then invented the Lawrence Fitzgerald, the length contraction, and that's how he went into the history of physics.
So 10 years later, Lodge was performing experiments on lightning protection when he noticed that discharging capacitors along wires and he found that he could realize spectacular sparks. He correctly deduced that this was the action of an electromagnetic wave in resonance. So now, confident that he was generating and detecting electromagnetic waves, Lodge planned to report these outstanding results at the meeting of British Association. But right after he returned from vacation in Aarhus. But when he was in the train and traveled out from Liverpool, he discovered the new article in Annals of Physics by Henry Kertz on electrodynamic waves in air and their reflection. It says that you don't have go to the vacations. You must work. You must work and publish your papers. So Henry Kertz worked on the subject in Karlsruhe, and he noticed that something curious happened when he discharged a capacitor through a loop of wire. An identical loop a short distance away developed arcs across its unconnected terminals. Hertz recognized that the sparks of the unconnected loop were caused by the reception of electromagnetic waves and had been generated by the loop with the discharging capacitor. And inspired, he used sparks in such loops to detect unseen radio frequency waves. He went on to conduct experiments to verify that electromagnetic waves exhibit light-like behaviors of reflection, refraction, diffraction, and polarization. Also, he performed a host of experiments both in free space and along wires. He demonstrated that electromagnetic waves were transverse. They oscillate just as light does, in a direction perpendicular to the direction of their propagation. So, Hertz showed that there was likely an entire universe of invisible electromagnetic waves that behave just as visible light does, and that move through space at the same speed. This revelation was enough for inference for many to accept that light itself is an electromagnetic wave. So eventually, scientists accepted these waves would travel through nothing at all, and the concept of a field at first distasteful because it lacked any mechanical parts to make it work, becomes central to much of modern physics. There was much more to come, but even before the close of the 19th century, thanks to the dogged efforts for a few dedicated enthusiasts, Maxwell's legacy was secure. Thank you for attention, and may the electromagnetic force be with you.